Hi, welcome to part 4 of my boosted flashlight project. Today I'm going to be going over using or creating pulse width modulation using a 555 timer. If you remember from last time, and through all the videos we've been talking about this boost circuit, we need a pulse width modulation signal to operate this N MOSFET. And how do we generate that? Well, in the scheme I'm using for this project, I'm going to use a 555 timer. I put this slide just kind of as a reminder that what we need the 555 timer to do is give us a square wave with a duty cycle of 90%. And so what exactly is a 555 timer? Well, it's an integrated circuit, and it's a very versatile integrated circuit. I guess it's actually the most popular IC ever created. If you go to Wikipedia, you can learn all about this thing. And in fact, all the information I'm going to present today, I pretty much took out of Wikipedia. If you scroll down through it, you'll find out that it has 3 modes, which are astable, monostable, and bistable. I'm going to briefly go through all those, but Wikipedia is nice. It presents you all the equations for each mode, and it gives you like a simple breakdown with graphs and circuit diagrams. Okay, so yeah, it's got the 3 modes: astable, monostable, bistable. The first one is astable, and in astable operation, the 555 timer creates a continuous square wave at a certain frequency, whatever frequency you set it to. And you can set the high time, the low time, and the frequency using 2 external resistors and a capacitor. So once you have your circuit connected to your 555 timer, the output will be a square wave, which is what we want, and you can set the pulse width so while it's high, so the time that it's on and the time that it's off, and also the frequency. So that seems pretty handy for what we want to do. It's also got monostable mode, and again, all 3 of these modes are what make this such a versatile circuit, because it's one chip you can buy that's been around for forever, so it's very robust and it's very inexpensive, but it can do several different things. And so it's basically an electronic oscillator in the astable mode, the previous mode. This one, it basically lets you create an electronic oscillator, so you could use that for turning a light on and off, like blinking it, or you could use it to generate a square wave that gives you like a tone. So if you wanted to have like a speaker generate a 400 hertz tone, you could do that using a 555 timer. Monostable mode is a one-shot pulse mode, and I've actually seen this a lot at work, but basically what a one-shot pulse does is when a certain input trigger signal changes, then the monostable one-shot pulse generator will generate a pulse of a defined width when it sees that change. And this is handy for things like button debounce, or if you just want to like detect anytime you want to have an output come on for a while after an input's given to you. And again, this the length of time that this pulse operates for, you can set using an external resistor and a capacitor. And the last mode that these things are mainly used for is the bistable mode, and that's basically it just turns the 555 timer into a big discrete flip-flop. So what that means is the output's a reflection of what is on the trigger and reset pins, what it was or what it changed to. So for example, if the output was coming along at low and then we got the trigger signal went from high to low, then the output will jump to high until it sees a change in the reset, and so on. So yeah, for our purpose today, we're going to be using the astable mode. And here is a basic breakdown of the equations that are going to govern this thing. Here is the circuit for it. This is the astable circuit. I pulled this off of Wikipedia, but it's pretty simple. It's just a 555 timer, so the little box, this thing, and then you really just need these 2 capacitors and these 2 resistors, and of course like a voltage supply. This 10K resistor out here I'm going to be using as a load just so we can see the change in the voltage out here. But so we have R1, R2, and C. Those are the only things we really have to play with, because this 10 nanofarad capacitor, that's constant. It just needs that on the control pin, and this 10K, like I said, is our load. So these are the 3 variables we're looking at. And So in astable mode, these are the three equations that govern the operation, so that determine what the square wave is going to look like, and they're all a function of, well, they're a function of those three variables, R1, R2, and that capacitor. So for us, we want to somehow derive a square wave with a duty cycle of 90% from these equations. And I know the first few times I tried to solve this, I went through like all kinds of algebra saying, oh, I want to set my frequency to be something, so I tried to set a frequency, and then, oh, I know I need my low to be this percentage of that frequency and the high time to be, and it just turned into an algebraic mess. So the easiest solution I found for using a 555 timer as an astable oscillator, or in astable mode as a pulse width modulator, is to simply look at, well, I know I need a duty cycle of 90%. And what does that mean in terms of timing? Well, I know the amount of time that my wave is high is equal to about 9 times the amount of time that my wave is low. And basically you can think of that as if my wave was composed of 10, if I split my total period into 10 sections, 10 even sections, then basically 9 of them would have to be high and 1 of them would be low, so that would give me 90%. So if you go back to the equations, I have an equation for T high, and it's a function of C, R1, and R2, and I have a equation for the low time, which is a function of just C and R2, and those are those same equations right here. So using this times 9, using this fact, just given that a duty cycle of 90% will do that, I can set it up as the high time is equal to 9 times the low time. But very conveniently for us, you'll notice that the ln of 2 cancels on both sides of the equation, C cancels on both sides of the equation, so you're left with one equation in terms of R1 and R2, and it boils down to just R1 is equal to 8R2. And at this point, it's actually kind of arbitrary. I can pick whatever values I want that will get me close to real world values of resistors I need. There is one caveat when using a 555 timer. The R1 variable needs to be able to handle, like, have a power capability greater than VCC squared divided by the resistor value. So the higher R1 is, the more efficient your circuit's going to be, and also the increase of likelihood that you'll satisfy that power requirement. But it also does change your capacitance value, obviously, because, well, if you look into how a 555 timer works, it makes sense. But these will change the capacitance value, and again, they're all linked in the equations. But at this point, I just arbitrarily said, 80K is going to satisfy that power capability of the resistor, VCC squared divided by R1. Easily, I can handle that. And then this is just a nice ratio. It's 8 to 1, so why not just choose a 10K for my R2 and an 8K or 80K for my R1? And then it's not going to make sense at this point in the design, but later on I'll make it evident why I would want a higher frequency for my pulse width modulation. So I just went for an even, easy capacitance value that gave me a frequency that I liked. So in this case, I discovered that 100 picofarad gave me about 143 kilohertz frequency, and I thought that was a good enough value. And again, I'll make that more apparent in a later video, but once I figured out what resistors I needed, I just changed the capacitance until it gave me something that I liked. And so this is going to be the final circuit that we're going to design today, and it is just the 3 volt voltage input, those resistances and capacitances we calculated, and then just the standard 555 astable circuit after that. So I'm going to go into OrCad. This is the same project that I left off in the previous video, and today I'm going to show you how to create a new schematic and then simulate that schematic instead, because last time I left you off with schematic 1, page 1. This time we're going to create a new schematic. I don't want to create a new page because the folder of a schematic, it contains all the pages, but all those pages are simulated simultaneously. And in this case, I don't want to design my boost converter. I just want to focus on the pulse width modulation circuit, my 555 astable circuit. So today I'm going to make a new schematic, And how we're going to do that is you click on the top project DSN, right click it, and then go new schematic. Here your option is to give it a name, so I'm just going to call it my PWM for Pulse Width Modulation, and it gives me this new folder. That's the new schematic. So I'm going to left click on that, right click, and then go new page, and that's going to be page 1's a fine name, but I'm just going to set it to PWM. I just usually set it as the same as the schematic name, and then double click on that to open it, and we're given a nice blank clean slate here. I'm going to try and get this so you guys can see more of it. Alright, so I'm going to start drawing this thing. So pretty much the same as last time. I'm going to go place, piece-by-piece component, and we'll get our resistors down. This is the wrong orientation I want, so again it's Control R. I'll place that guy, and then I know I need one more out here somewhere, so I'm just going to drop it. And then I'm going to hit Escape to exit placing resistors. I'm going to go back to Part, piece-by-piece component, capacitor. We'll get those bad guys put down. Again, it's the wrong orientation, so Control R, rotate that thing around, and I know I need another one around here somewhere, so I'm just going to drop it. Okay, I'm going to hit Escape to exit placing capacitors. Then I'm going to go place piece-by-piece component. I'm going to go source, and we'll grab our voltage source, just the DC one. And again, that is that nice our 3-volt supply, because that's what our batteries are going to give us. And then now I need the 555 timer. Now how the heck do I find that thing? I didn't show this in the last video, I think, but to find components that you want to use, you can either use that place, like the P key that I talked about last time where it opens this thing up, and you can try and search for 555, and if you have the right library it'll pop up. So I think if I go 555, it will give me 555 alt, B, 555C, 555D. When I first got OrCad, it didn't give me this 555D, and that's the one we're actually going to be using today. I had to go out and find that it was in the eval library and import that library, and it was a huge pain. So I don't recommend this for looking up parts. What I recommend is you go place, piece-by-piece component, and then go down to search. And this is a beautiful feature inside Cadence. You can go by category, so if I wanted to look up discrete components, I could go bipolar transistors, I don't know, let's go power, and then you can go NPN, PNP, and it gives you a list, and you can look at the parts, and these are often real-world components that give you a somewhat accurate SPICE model, so that's a great thing. But we're not interested in any of that today. I just want to find my 555 timer, so I'm going to come up here and type in 555, hit enter, and it gives me this list. Now here's a 555 timer with some other things. Another limitation that the trial version of OrCad has is that it only lets or allows for a certain complexity in your SPICE models. So if you use some of these, I think like 555B or 555C, if you put that in your circuit and you build it and you try to simulate it, it's going to say you have too many components in your net list, something like that, and it basically means that you have too many things on the schematic for the light trial version. So the one we want is this 555D. I think it's a simplified model. So just come down so your mouse is on the 555D, double click that thing, or maybe single click it until you get the finger, and then double click to grab the component, and then just come out here, drop it down with a left click, and then I'm going to hit escape to exit placing 555 timers. And I'm going to exit this to get a little more real estate back. Okay, last thing I'm going to do is place my grounds before we wire this up. So I'm going to hit, I can hit the G key to pop that up, or I can go place, ground, and again I like to use this 0 cap sim. So I click OK, get one for the power supply, one for this branch, one for that, one for my ground pin, one out here on the load. Okay, I'm going to grab my wire, and we'll wire this thing up hopefully pretty quickly. I don't want to make this too boring. I didn't know about that search feature like the first few months I was using Cadence, and so I was going into those libraries like one by one looking for the components I needed. This goes to control, and it was a huge pain. When I found that thing, man, I was overjoyed. It was actually my coworker showed me that thing, and it just saved me a ton of time. Okay, so now I need to take this trigger, bring it down, connect it to above the capacitor, and it gets shorted to this threshold pin. Okay, discharge goes to in between the resistor branches. Okay, and then reset goes to power. Okay, ground goes to ground, obviously. Here's our output pin. That's going to come to that resistor, and that's going to go to ground. Alright, and I'm going to start populating these values. So I got 3 volts DC on the input. If you remember from our calculations, this was an 80K resistor. This guy's a 10K. And we're going 100 picofarad on that bad guy. I think this is a 10 nanofarad. Okay. 1K is fine out here for just testing. Alright, so that looks pretty good. I'm going to hit save. I forgot to do that last time. Actually, if I open this page 1, it's blank. So I didn't want to confuse you, but so now in order to simulate this thing, I need to make it the root of the project. Since I split up my design into several schematics, it needs to know which schematic I'm interested in simulating. Again, if you have multiple pages inside a schematic, it's going to simulate all the pages at the same time. So since I wanted to split my project up so that I could simulate the boost converter separately from the pulse width modulation circuit, I have 2 schematics, so it needs to know which schematic I want to simulate. So I'm going to left click on this folder, the pulse width modulation folder, then right click and click this make root. And it's going to warn me you have to save your design. I'm going to say OK. It's going to save and close everything. But now you'll see over here this slash icon on the folder is on the pulse width modulation before it was on the schematic. That indicates that this is the root schematic in the project. So that's the one it's going to look at for simulation. So I'm going to reopen that circuit, and now it should be ready to simulate. But I'm going to create a simulation profile. So go to PSpice, and then new simulation profile. I'm just going to type in a pulse width modulation transient and hit create. It's going to pop up this menu. Today we're only simulating out to 50 microseconds. Leave it as a transient. You don't need to do anything else. Hit OK. And just to double check, yeah, since it's red, I know that that is the what do they call it? The active simulation profile. So the last step I'm going to do is just add this voltage probe onto the output because I want to see what it looks like. And then I'm going to hit run. And it looks like it's finished. Let's maximize that. Alright, so we got a nice square wave here. It looks a little funky at the beginning, but I think that's just because the part is like powering up. So I'm going to zoom in on the area we care about, which is just one of these pulses. And I want to take some measurements to see if we're somewhat accurate. So what I'm going to do is left click just to make this the active window, then right click and go to cursor on. And again, that gives me these, if I left click I get the red cursor, I can drag and place that somewhere. If I right click I get the green cursor. Now that made it a little hard to see my waveform, but what I'm going to do is right click and come over to like the low section. I want to measure the time low, and then right click to drag the green one. And I'm just going to view this. The difference between the two is the amount of time. So that's about 874 nanoseconds, which is 0.874 microseconds, if you remember. So my low time is about 0.874 microseconds. And the high time, I've got the green cursor on the beginning of the high, so I'm going to take the left cursor, the red one, with a left click and bring it to the other side. And that guy's about 7.007 microseconds. So the high time 7.07 microseconds, and the low time was 0.86, I think, microseconds, something like that. So does that make sense? Let me see if I can. Let's take a look at the calculation and see if that makes sense. So if we think about what we just got, the high time was about 7 microseconds, 7.07, and the low time, I guess I wrote down a different number, but it was about 0.852 microseconds, somewhere in that ballpark. I think it was 0.86, but so our duty cycle is just simply the amount of time that it's high divided by the total time. And if you do 7.07 divided by 7.07 plus that 0.852, you'll get a duty cycle of 0.892%, well, 0.892, so about 89%. And if you remember, we wanted it to be 90, so we're pretty dang close. And if you take a look at the frequency, you can get the period by adding the low time and the high time, which is about 7.922 microseconds. If you invert that number, you'll get a frequency of 126 kilohertz. So in calculation, I was expecting to get a duty cycle of exactly 90% and a frequency of about 143 kilohertz. But according to simulation, it's going to be more along the lines of a duty cycle of 0.892 and a frequency of 126 kilohertz. Honestly, for the application we're using with the flashlight, it's not going to be a big deal. It's nothing. This isn't like a critical circuit. If you needed better timing, a 555 timer might not be the best option. There's other circuits out there specifically designed for that. But this is such a useful circuit. It's one I want to get really good at, and it's one I thought would be a good thing to introduce to people interested in electronics. So that's what I'm going with, and I think those values are going to be just fine for this circuit. So that's it for today. Let me think. Next time I'm going to be drawing the finished schematic so that we can start selecting components and get into PCB layout. So thanks for watching, and I hope you enjoyed it.